is we want to try to answer this question. How does one get into a state of weightlessness? Well, we could talk about astronauts. Astronauts, we see them floating in space. That word floating is a very deceiving word. So we should be careful how we say that word. Again, there's misconceptions here. And so here's what we find here. What I'm going to do here is that to try to explain how one gets into a state of weightlessness, I just want to remind you here. So remember, free fall means only the force of gravity acts on you. Okay, that's what free fall means. There's only one force acting on you, the force of gravity. So to try to give you a sense of how you get into a state of weightlessness, what I'm going to do here is I'm going to give you an example. So suppose a baseball player throws baseballs. But we're going to be a little bit more clever this time. And what we're going to do here is that we're going to set up a tower. So we have a tower. And when I think about this tower here, we're going to imagine that it's above the ground. And now we have somebody that's going to be throwing the ball. So when I look at this ball here, right, here's the windup. Now, how do you draw somebody with the windup? I have no idea, but I imagine that the elbow's back, and then we're going to put a red ball right here, and then the other arm may be down here. And so what we're going to see here, since he's a baseball player, we have to put a cap on him. So now, what happens? If you throw the ball is going to follow this curved path. But if you throw the ball faster, the ball has to travel farther. And if I continue to throw it faster and faster, it's going to have to go farther and farther and farther here, right? So then here's my questions. If one throws the baseball fast enough, one must account for the curvature of the, I should put that in capital words. You have to account for the curvature of Earth's surface. You have to account for that. So here we go. Let's talk about the curvature. So the curvature of Earth looks something like this. So we got to be careful here because the curvature is different for different heights. And that may sound like a funny remark here, and that's because the force of gravity varies as you go up to different elevations. So the numbers that I'm giving you here is that these numbers are for sea level. And so here's what you find. So when you look at the curvature of the Earth, you have this curvature. So the question is that how much does the Earth curve? So if I go and I look at this thing, we're going to say, okay, here's the Earth. We know that the Earth is almost a circle. So by how much does the Earth curve? So it turns out that if you travel, let's say this distance, and what you find here is that if you travel 5,000 meters or 5 kilometers, that the Earth now drops away from a straight line 5 meters. And there's two, so what we say here is this. So it says that the Earth's curvature falls off by 5 meters every 5,000 meters or 5 kilometers. Now there's something special about this 5,000. And so I cherry picked that 5,000. And this is the reason why I cherry picked it. So now imagine that we're going to drop a ball. So if you look at the ball, here's the ground, right? So that's the surface of the Earth. And then I have that red ball. And if I drop a ball from a height of 5 meters, it turns out that the fall time of a ball dropped from 5 meters is 1 second. And that becomes important. So in order for the ball to hit the ground, it's going to take 1 second for it to fall 5 meters. Now this number, 5 meters, it's kind of an out there number. So here's just a silly fact, but a pretty cool fact. So let's imagine that we have the Earth again. So I'm going to copy this, and I'm just going to bring it down here. So what you see here is that if you're standing, okay, so what we're going to do here is that we're going to imagine that you're standing here. You're standing here on the Earth, and you're looking out over the ocean. So your line of sight goes like this. So this is your line of sight. Now what you'll find here is that when you get to 5,000 meters, what I said here is that the Earth falls off by 5 meters. So if I had a boat, okay, so let's imagine that you have a boat right here. And when you look at this boat, what you're going to see here is it has a sail, and the mast, let's say, comes up to this distance right here. So then, of course, you might have a sail here. And if the mast, so if I measure this height from here to here, if this is equivalent to about 5 meters, it's about 15 feet. What you'll see here is that you will barely see the tip of the mast, because now you have to account for the curvature of the Earth. And what's really surprising is Newton understood all of this about the curvature of the Earth when he was just a teenager back in the 1600s. Nobody had ever thought about this. And in fact, there's something known as Newton's mountain. And what we're going to do here is to try to show you what I mean by that. I'm going to use an app called Newton's Mountain. And so here's what we have here. So Newton's mountain looks something like this. Okay, so when you're looking at this thing, you could see, note that there's that mountain right there. By the way, this is Newton's own manuscript that he wrote in the 1600s. This is an image from it. And what you're seeing here is that what I did here is that I did that platform where the baseball was being thrown off of, but here you could imagine that this is a cannon that's shooting a cannonball. And again, there's no air resistance here. Now, the thing that's different here is that look at this elevation. This elevation is 7,500 kilometers. When I did the elevation, remember what I said here, that we were at sea level. So the numbers vary from what we just discussed because of the elevation. So let's check it out. So if I shoot it, you could see that it doesn't go very far. But if I go faster, you could see that it goes further. And if I go even faster, it even goes farther. But the question is there a sweet spot? So maybe I should step back here and try to explain what it is I'm trying to show you here. So what you're doing here is that if I just took a screenshot of this thing, and let me go back and share my screen with you before I continue on. So what you're seeing here is what's happening here is that the ball is not moving fast enough. And as a consequence, the ball falls into the earth. Okay? The ball falls into the earth here. Now what I want to go do here is that I want to go in and continue that applet here. And so when you look at the applet, what I'm going to do here is that I'm going to now go even faster. And there's a point, let's see if it's 7,000 meters, that if I shoot it just right, look what happens. It goes all the way around. So in this situation here, what you're seeing is this. So you could see that I have this image here. Let me make this just a tiny bit bigger. What you find here is that if it's moving fast enough, so if the object is moving fast enough, so at sea level, this number is what? 5,000 meters every 1 second, 5 kilometers per second. This is equivalent to 18,000 miles per hour. So if an object is moving fast enough, it has to be moving that fast. And remember, that 5,000 is not a surprise because I chose that number because 5 meters means 1 second to fall. So if you do that, so if it's moving fast enough, the object, instead of falling into the earth, now falls around the earth. Which then means that it's constantly missing it because it's overcome the curvature of the earth. So if you move 5,000 meters a second, then what happens? The earth continues to curve. So the only way you can be in a state of weightlessness is that you have to keep missing the earth as it's moving here. So what we say here is that the reasons why the numbers are different is because they have different, they're farther apart, so that means it has a bigger radius. So here's what you find here. Then any satellite / space station is moving fast enough that they are in a state of free fall. Oops. Well, wait a minute. What is free fall? Weightlessness. So check it out. Any person in free fall is not floating, but falling. They're falling down. And the thing about it, it appears like floating because everything around this person is also falling. So it seems like you're defying gravity, right? You're in a state of weightlessness, but you got to remember, you're falling. You're not floating. So what we do here is that probably one of the coolest things that I can remember was a guy by a name, an astronaut by the name of, I believe his first name was Bruce McInnes. And sadly, he recently died, but he was an amazing astronaut. And there's lots of things to talk about him, but this was one of the coolest things. And it's this image right here. And what happened here is that you have the Earth. And so now the satellite, in this case, is what? It's the shuttle in orbit. So the shuttle, space shuttle, is moving fast enough. Now note, if you're at, so these I think the shuttle, what they do, I think they're somewhere around, like, I forgot how high they are, like 35,000 kilometers. Note that airplanes fly at 30 kilometers, 35 kilometers. but they're like at 35,000 kilometers. So when you look at this distance here, this distance is about 3,500 kilometers. Okay, which is quite different than airplanes, much, much higher. And what you see here is that this is what's happening. Well, you have the shuttle. So if I look at the space shuttle here, the space shuttle sort of like moving through space right here. And so what Bruce did is that I should write the space shuttle because I don't know if that looks like a space shuttle. So what Bruce did, he untethered from the space shuttle. And the back of him has that jetpack. So he literally, he jetted. So you can imagine, here's the little jetpack right there. He jetted in front of the space of the shuttle. And so what you're seeing here is that now he's moving faster than the shuttle, just a tiny bit. And so what happens here is that if you were to measure his speed for this height, well, guess what? Well, he's moving like this, but then the force of gravity pulls him back down and he keeps going in a circle here. And so he's constantly falling towards the earth, but he's moving fast enough that you have curvature. And I think that image is, I'm very fond of that image because I remember when he did it, and it's always been a really great pleasure to think about this.